Yeah, thank you very much for the invitation. It's a great pleasure to be my first time in Brazil, and I'm really enjoying it. What I want to talk to you about is optimal control of multi-physics systems. And so let me start with an introduction. So modern key technologies in almost all areas of mathematics need modeling, simulation, control, and optimization of complex dynamical systems. And most systems that you look about today are multi-physics systems with different accuracies and different scales. And nowadays, in particular in many areas of technologies, modeling becomes highly automatized. For example, in circuit simulation, you know when you generate a new chip, there's nobody that can look at this anymore. It's automatically generated by a program that generates a program and others. And similar things happening in mechanics nowadays. And what I'm going to tell you is a direction into that a new modeling, simulation, and control paradigm is needed that combines these technologies. Okay, so if you look at packages that are available right now, for example, Simulink in MATLAB or SPICE-like circuit simulators, they proceed as follows. They start with little elements. Like in SPICE, they start with, say, capacitors and resistors, or in mechanical system, you take, what you do is you puzzle the total model together from little pieces. So you start, and then you put them together with a network and a graph, and you typically model each single part, which we call a uniphysics. So that's one single component, and then you put two together, and then three, four, and in modern technologies, millions of parts together. And the numerical simulation or the control is done on the full model. And that's typically called a descriptor system, at least in the terminology in engineering. So what is a descriptor system? A descriptor system is a differential equation, or more exactly a differential algebraic equation, which is an implicit system given by a function f of t, x, u, and x dot. X dot is time derivative, u is an input function, t is time, x is the state. You have typically an initial function or initial value, and in most cases you also have an output. Like in a computer program, you have an input, something you put in, and something you take out. We will not worry too much about the output here, but in general, the system looks like that. And f is a function that's typically continuous, but it could also be piecewise continuous from some domain into some vector space, RL. And the state could be infinite dimensional. So if you have a PDE in the background, the state is infinite dimensional. So let me start with two application projects. Unfortunately, I cannot show you the movies now, but this is the first one that I want to talk about. This is a collaborative research center. It's one of the flagships of German science funding. This was a joint thing called Control of Complex Shear Flows. And the question was, can we do the following? So I have a channel here. I have some input that comes into the channel, so flow. And the question is, if I blow or suck air here in the corner, or I use a loudspeaker, can I move the so-called recirculation bubble? I hope you can see that. There is the streamlines of the flow, they recirculate here after the step. And what's happening is you want to somehow move this so-called recirculation bubble around. You want to move it back and forth. And you have some sensors here, which are typically either microphones or some heat wire measures that allow you to tell where the bubble is. and then you can move it around. That's a typical model problem. It's a very simple model problem. It's used as a model problem because one knows the analytic solution about this, but the real application is that you want to control the flow on an airline wing. And you probably will, in about 5 years, all fly with airplanes which have that in there. So this has been a joint project at the end of the research with Airbus. And Airbus now will put, and I will show you some results at the end, will now put little actuators into the wing so that when you get into turbulence and the flow detaches from the wing, that's when you have this thing, that you reattach the flow to the wing very quickly. So that's the goal. So this example that I showed you is a test case. That's where we know everything, and we can do this, and we control it. But in real life, it's put into an airplane wing. So what you have to do is you have to model the turbulent flow around the wing, and you have to develop control methods for these large-scale coupled systems. And coupled, why? Because you have the structure of the airplane, and you have the flow around the wing. It's really a fluid structure interaction problem. Now, if you want to control this, and you want to do it in real time, very quickly, you need to reduce the model because it's a 3D flow, and the computational method would drive you crazy if you would, and every airplane would have to have a supercomputer on board. So that cannot be done, and you have to build some sensors in. And so that's the first problem. And the second problem was a problem that I was doing with Mercedes, with a Daimler. And so if you have enough money to buy yourself an E-Class model in 2017, you will have in the automatic transmission in there, you will have one of the methods that I will talk about implemented. So the idea was to do a software-based control. Why you want to do software-based control? If you want to do, as typically nowadays, it's hardware controlled, so it's controlled with a chip that sits directly in the transmission. You want to do it with software because you want to be able to reduce the cost in production. Because otherwise, the transmission has to always be produced in the same very accurate way. That's expensive. And the mathematics and computer science is completely cheap compared to that. So if you can put it on the board computer, a controller for your transmission, then it's really cheap because you put in a CD, copy a CD, and then you can do it for every single one. So I had a movie of the transmission, but it looks like this. So it's a complicated mechanical structure, and the main part is such a half toroid, which is essentially these two conic things which are pushed back and forward. And that's an old model. That's not the one that will be in the Mercedes because I'm not allowed to show that. But this is a one from Nissan, which is publicly available. But so essentially these things are pushed in and out, and then this thing are pushed out. And it's a continuous transmission. So it doesn't have 1, 2, 3, 4, 5, but it continuously switches between the gears. And so you have a hydraulic system. So you have these parts which push these conic parts together. And inside the conic part, you have this thing. So what you have to do is you have to model the multiphysics model, which is a multi-body system, the elasticity of the parts, the hydraulics, the friction. And you have to develop control methods which run on a board computer in 2017, which would probably be a PC, something like that. So, and you want to do it in real time. And clearly you want to decrease the fuel consumption and improve the smoothness of the switching. So that's state of the art, how in engineering things are done. So in this way, because of these automatic modeling packages, modeling has become extremely simple. So you just have a Lego box, you have all these models on the side, you click, 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 put them together as a network, and everything is easy. The problem is finding good initial conditions for your simulation. And what also can happen, and that's even worse, is that the system may be unsolvable, even the discretized system, so the DAE that you solve. And then you have a typical thing called the drift-off phenomenon. I will give you an example for this. So when in the early 70s, the German company Siemens produced the high-speed trains for Germany, in the simulation they would always fly. This is the drift-off. So what do engineers do when things start flying? They make it heavier. So the German model, ICE-1, is much heavier than the TGV in France and uses much more energy. And this was a simulation error. And it was not an error of the design. It was a simulation error. And this phenomenon, I will talk about this in a minute. Model reduction is extremely difficult for these differential algebraic systems, and classical control is almost impossible. And the real problem is this black box modeling, putting everything together by pieces and with interfaces is wonderful from the modeling point of view, but it's awful from the point of view of mathematics. Neither from the numerics nor from the control so what we can deal with it. What can we do about it? Keep the modeling as easy as you can and allow the engineers to use these boxes of model tools, but make the model better for numerics and control. And what in particular has to be done is a balancing between modeling, simulation, and control errors, and at the same time make it as automatic as possible. There's a new language now available, and MATLAB is also putting a new code out. So this is called Modelica. This is a modeling language which will probably be the standard in a few years because it's open source. And SimScape is a corresponding version of the MATLAB company. Okay, so that's just for motivation. Why do we need to study differential algebraic equations, these general systems? So now I give you a crash course in the theory of differential algebraic equations. Okay, so we have such a system, a differential equation, implicitly given. So you cannot typically solve for x dot because the Jacobian with respect to x dot is singular. That comes from the fact that you have algebraic constraints which cannot be resolved for x dot. And we have an output. And what you typically do is you form a so-called behavior vector. Is you take z, which is you just put all the variables together. So either x and u or x, u, and y. And then you get a general system of this form. F of t, z, and z dot equals 0. And that is the vector of all the variables, whether they are inputs, outputs, states, or whatever. You just put everything together, and you can imagine this is a very large system. And together we have a set of initial conditions, which are all the conditions that were given before, plus whatever constraints, mathematical constraints appear. Let me give you an example so that I will take this example all the time. This is the simplest case of such a differential algebraic system. That's a cleaning robot. So that's used everywhere in industry to smooth a surface, to weld, and to clean. So here is your car that you want to polish the surface. Here is the robot, which is fixed here, and it has 3 arms. And you want to clean it here. So you want to move this thing here up and down, typically on a surface which is not even straight. And you want to do it in such a way that the pressure here is not too large and not too little. So you want that it really becomes clean, or do the welding. And then you have constraints here in this parts because the angles cannot, the parts cannot separate. So for example, what you get is the Lagrangian equations of motions. So m of theta is a vector of joint displacements, times theta dot is c. That's the vector of centrifugal and Coriolis forces. M is mass, and g is gravity, and then you have a control input. And since you have a constraint, the parts have to go together, and at the end and at the bottom the thing is fixed, you have some algebraic equations for the angles. And so that's the differential algebraic equation. That's the most simple one in a mechanical system. And the constraint function is some nonlinear function. And for the output, you typically have some tracking. You want to follow a certain curve. So I didn't say that. And this capital psi is just the Jacobian of this constraint function with respect to the angles. So you have constraints in the joints and the position, and of the force of the tool at the end where you want to. These are the constraints. And the problem is that not only the force and the constraints are constrained, but their derivatives are also constrained. And also the second derivatives. This is just because if you move something and the position is constrained in a certain direction, then also the velocity goes in this direction and the acceleration goes into this direction. So the solution depends on derivatives of the constraint function. Not only the first, but the second and the third, not only the position, but also the first and second derivatives. And that means it needs higher regularity requirements. It needs to be smooth enough. And standard numerical methods do not keep these hidden constraints, and that means you have this drift, these flying trains. And the control problem may not be solvable. So what do? So you take your model, and you reformulate it. You know that somehow internally there are some derivatives that have to appear. You don't know where, you don't know which equations you have to differentiate. So the brute force solution out is you differentiate everything. So you differentiate the whole system. So an F mu here means that you take the whole system and differentiate it mu times and put all the equations on top of each other. That's called the derivative array. And that was introduced by Steve Campbell in '89. So you take all the original equation, all derivatives, and you stack them into a big system. So it was non-square anyway, so now you get an overdetermined system of equations depending on variables up to the mu plus first derivative. And in the following, I denote by F mu psi the Jacobian, the partial derivative of f with respect to these variables. Now, this is an algebraic system if you don't consider this to be differential variables. So if you say that z dot is an algebraic variable, that's a nonlinear equation. And that has a solution set as a nonlinear equation, which describes a manifold, typically. And that manifold is somehow the solution manifold in which everything lives. That keeps the constraints of the positions of the derivatives up to whatever level. And that's the solution manifold that you would have to consider. And then you have here, it's a pretty terrible slide. In the linear case, it would be much easier, but in the nonlinear case, you have to make some assumptions that you can solve. So the assumption is the following. There exist integers mu, that's the number of times you differentiate, r, a, and d. R is a rank, A is the number of algebraic equations, so that all the constraints that are implicitly given in the system, and D, which are the differential equations, the dynamical part, and V for vanishing equation. These are the redundant parts of the system because you have now differentiated lots of equations, so some of it will be redundant, and such that for every vector in this solution manifold, considered as an algebraic system, the following conditions hold. This solution thing forms a manifold. It has constant rank R on this manifold. And there's some rank conditions here. And we have that this matrix F mu with respect to the variable z dot up to z mu plus 1, that has constant rank R minus A on the manifold. And then you can find, since you have constant rank, you can find locally a coordinate system, or even an orthogonal coordinate system, to do the projection so that you find the kernel from the left, and then you find the full rank part here, and you find another kernel, and then some other rank condition. This is just an assumption, but the main thing is the following. The hypothesis implies locally the existence of a reduced system given in the following way. F1 of t, z, and z dot. So that's somehow the differential equation. These are d equations. And these are the algebraic constraints. So you pull out of that complex system of equations and derivatives, you pull out some algebraic equations. These describe all the constraints that are there algebraically, and some differential equations. And the smallest mu for which the hypothesis holds, that's called the Strangeness Index. And for those who have heard about DAEs, that it essentially gives you the number of derivatives that you have to do to get this information. The good thing about this is still the same solution Z. So you haven't changed the solution. You just have taken the equation plus derivatives, and you filtered out a new system of equations. D differential equations here, and A algebraic equation. Solution hasn't changed. Now, this is a mathematical way to do it, but it's not a very practical way to do it, because first of all, if your system is already 1 million variables and you differentiate it 3 times, you have 3 million equations, then 3 million equations. It's typically too expensive in many applications. In most applications, one actually knows what to differentiate, like in this robot example I will show you in a minute. And this derivative array is typically more equations than unknowns. And what one can also do is one can introduce new variables. So if you have too many equations and too little unknowns, you can introduce new artificial variables. And in most applications, this can now be done in an automatic way, but it's very technical. I'm not going to show you how to do this. And actually, we have patented this in the context of circuit modeling together with the company NEC, Nippon Electronics Company, and they are using it in their circuit simulator. So, but let me explain this on the mechanical system. So I take the second order differential equation, like the one from the robot. I introduce velocity as the derivative of the position. Then I get this second order system. I take the constraints and add the constraints with a Lagrange multiplier to the differential equation. Here's my output. And now you see what happens. So this is a differential equation, the second order differential equation written in first order form. These are the constraints, and you know, because it's a mechanical system, if the position is constrained in one direction, the derivative of the position, which is the velocity, and the acceleration also have to be constrained. So what you can show and assume that this Jacobian has full rank and that the mass matrix is symmetric and positive definite, then you can show that this has Strangeness Index 2, so 2 derivatives are necessary to filter out everything, and the derivatives are just the derivatives of this thing. So you just add these 2 derivatives to the system. That's enough. But that's because you know it's a mechanical system and you know the information. In general, you have to filter this out yourself. Then now you have too many equations. You could either throw some equations away, which are unnecessary, which means you multiply here some projection, or you could also introduce new variables. So you find a permutation matrix pi such that this constraint for the derivative has a square invertible part. Then you partition the variables, introduce a new variable for P2 dot and for V2 dot, and then you get this system. And this system now can be solved with all the methods and can be used for control. So there is a simple way if you know the structure, but in general, it's hard. OK, so how do you do numerical simulation? Numerical simulation is very simple. You just take this derivative array, And in the nonlinear case, you have to estimate or guess how often you have to differentiate, except if you know from the structure. You can do that locally by differentiating, checking whether you can do it and keep going, but in general, it's hard. Or you use computer algebra, but that wouldn't work for a huge system. So you take that derivative array at your initial point, and you solve it algebraically. That's a nonlinear system which you solve. And for the integration, you just replace. This is your algebraic system that you have to solve, and that is the first equation. That's the original equation where you replace the derivative by some finite difference. Or it could be finite element if you like. And Z1 is the projection matrix. That's the projection matrix here. Where is it? Z1 is here, which pulls out the differential equations. So that describes the dynamics. And you don't need it exactly. It's enough to get a good approximation at the solution. And then the DH is just the finite difference or whatever type of discretization of the derivative you do. And then you can prove if F satisfies this nonlinear hypothesis, then the occurring Jacobians have full rank, and the solution, provided that the step size is sufficiently small, and this approximation to this projector is sufficiently smooth, then you can show that the simplified Gauss-Newton method converges, and the order and the convergence are the same as for ordinary differential equations. So the method can be implemented completely locally. You don't need information about the global nonlinear behavior. So that's nice. There are codes that are available. So there's a linear code for linear time varying system with variable coefficients, with BDF and Rumukutta discretization in time, and whatever you use in space. There's a nonlinear code, and there's a MATLAB code. And there's a special multi-body code, and there are circuit codes which were done together with NEC. So these codes are available, freely available if you write me a message. So I cannot show you the movies because the system doesn't work. But essentially, you can show with that and prove that it really keeps the constraints. So you stay on the constraint all the time. And so, for example, if you have a periodic system, this rolling ball, it comes back to the original point rather than flying off or drifting away. So it's like a geometric integrator where you stay on the manifold, except that the manifolds here are more complicated than in classical Hamiltonian system. Now you want to do optimal control. So how do you do that? So what is an optimal control problem? So you want to minimize a cost function there's a cost on the endpoint, capital T, and there is some function here that you describe. This could be energy, this could be minimal time, this could be smooth behavior, or whatever. So that is the general nonlinear function, and the constraint is like this. The output equation you can usually insert in the optimal control problem, and it goes away. So let's first discuss the linear case, because that's a little bit easier to understand. So in the linear case, you have a classical problem. So you have a cost function, which is a quadratic function at the endpoint, and it's a quadratic function in x and u. It's a classical optimal control problem. The W, S, and R are some matrices, and you have a constraint. And so in the linear case, such a differential algebraic equation would look like this. E of t is a singular matrix, which has the part that is describing the differential equation and the part which is describing algebraic equations. And this is a linear differential equation that you want to have as a constraint. So how do you deal with that? well, can't we just go to the famous book by Pontryagin and apply the maximum principle? The answer is unfortunately no. The problem is that for ODEs, under some Lipschitz conditions, the problem has a unique solution, classical solution, or in the PDE setting also weak solution for every sufficiently smooth input and inhomogeneity and every initial value. But this is not true for DAEs. Like, just take the train. The initial condition has to be on the track. It cannot just start from above and do a delta distribution to get down on the track. So there are constraints, and this makes these DAEs not always solvable. So you cannot just apply the maximum principle, because the maximum principle heavily relies on solvability. And the second thing is, because the initial conditions may be restricted, and because we need typically a solution space which is more complicated than classical C1 functions here, these are the difficulties. And if you try to do the proof of the maximum principle, even in the linear constant coefficient case, it doesn't go through. So you cannot just apply it. Here's a little example, just the smallest that I can produce. So you want to minimize x1 squared plus u squared, no endpoint condition, subject to such a differential algebraic equation. So it's one algebraic equation and one differential equation. At least it looks like this, but it isn't, because it has Strangeness Index 1. That means there is another hidden constraint here, and there's really no differential equation here if you look at it. And if you do the calculation, you get x1, u, lambda 1. They're both f1 plus f2 dot. And here you see that the solution may depend on derivatives. x2 is that. And the Lagrange multiplier that you get from the optimality system, this is equal to 0. So let's go back to Pontryagin and see what would Pontryagin do if you have an ODE. If you have an ODE, that's a well-known result. It's probably much before Pontryagin. I would say Lagrange, but it's not really in Lagrange. So if xu is a solution to the optimal control problem, then there exists a Lagrange multiplier function, lambda, such that x, lambda, and u together satisfy such a boundary value problem. That's the optimality system. And so that's your original equation. That's the adjoint equation. And here you have an initial condition. The adjoint condition is at the endpoint given, and this is the optimality situation. So if the R matrix, which was the weight for the input function, if that is invertible, then everything's fine. You can solve for u here. And what you get is, if R is positive definite, then we can solve for u and get the reduced optimality system. So you can write this as J times this lambda dot x dot is A at lambda x plus F0. And J is this matrix, and A is symmetric. So this is really the Hamiltonian Euler-Lagrange equations from classical optimal control. Now, so you can typically write this like that. So there shouldn't be dots here with a Hamiltonian matrix. And you know that the underlying flow is symplectic. That means it satisfies phi transpose J. Phi is equal to J for all. So that's a geometric flow. And phi is a fundamental solution matrix. So the naive idea that you can find in the literature, which is unfortunately not true, is you place the identity by E and then do the analysis in the same way, and then you would get such a system. That's the original equation. That's the adjoint equation. It has the E transpose here below the integral, and then this. And this doesn't work. Here is the example. The same example as before. This is the solution before. And if you just do this, try this system here, this naive idea, what you get is you see lambda 2, everything else is the same, but lambda 2 is f1 dot plus f2 double dot. So all of a sudden you need more smoothness. And also, you don't use the initial condition for the lambda. So that's really is something different. Then, depending on the data, this initial condition may be consistent or not, and you need more smoothness, and there are many other examples where this happens. So you cannot just apply it. So in order to go do this for the linear case, what you do is you introduce a special solution space. So I hope you can read this. E plus E, that's an orthogonal projector on the null space, on the range space of E. So the only thing you need that E plus EX is in C1. So wherever you have a differential equation, you need C1. In the other case, it doesn't matter. So E plus is the Moore-Penrose inverse that satisfies these three conditions. And U is typically a set of piecewise continuous functions or even distributions. And then you can show that the optimality condition looks like this. So if you take the optimal control problem and the system is strangeness free, that means you have already identified the differential and the algebraic equation, and the weight at the endpoint is in the co-kernel of the in the range in the co-kernel of E at the endpoint. And if you have a solution to the optimal control problem, then you have a Lagrange multiplier function, and you have an optimality system, which looks pretty much like the original system, but all these projectors are in there. And these projectors are absolutely necessary, and there's also an E dot here. I hope you can see that. Now, if E would be the identity matrix, then all these things come out, and you get the classical result from Pontryagin. But in general, you cannot. And the interesting result, and that's the most amazing result, I couldn't believe it, and when we proved it, is if all the data are sufficiently smooth and the formal optimality system has a solution, this naive idea, then you just change the Lagrange multiplier. So then there exists a function eta replacing the Lagrange multiplier such that the new system solves the correct, true optimality system. So that's very nice, because you can just try to solve the naive system. If this system, you get the correct x and the correct u, and you get the wrong Lagrange multiplier. Now, whether this is important or not is a question, because in some cases, the Lagrange multiplier means something. For example, in inverse problems, the Lagrange multiplier have an important reason. Also, they describe the force that is acting and the constraints. So if you want them correctly and you want to know these forces, you better solve this complicated system, which means you have to compute the projectors. Otherwise, you can just solve this replacement system. Okay, so that's nice. Now, just a few comments about the structure of this system. If you look at it for a second, in the constant coefficient case, this optimality system has a matrix pencil associated with it, which is a skew-symmetric and a symmetric matrix. Like in the Hamiltonian system, J is skew-symmetric, and the other matrix is symmetric. So it's a skew-symmetric symmetric system. That's called an even pencil nowadays. And you can actually show in the variable coefficient it's not skew-symmetric symmetric anymore because of this E dot term that appears. On the other hand, you can show that the boundary value problem associated with the optimality system is associated with the self-conjugate differential operator. So you write down the correct spaces, and you do the function analysis, and you show that this is a self-conjugate operator, the differential operator associated with it. And in this setting, this self-conjugacy is in the correct dual pairing. That's the right structure to look at, and that generalizes Hamiltonian system. And actually, you can show even more if some constant rank conditions hold, then there exists a Hamiltonian subsystem. And if the DAE is regular, that means it has a unique solution, it's a well-posed problem, then the underlying flow is still symplectic on the constraint manifold. So it's a symplectic flow on a constraint manifold. And these results also hold in the nonlinear case, but I skip this here because it gets too technical. So in the nonlinear optimal control setting, what you do, we know that from this strangeness-free or this reduced problem that you filter out of this derivative array, locally you can get such an algebraic equation and a differential equation. That's what I mentioned. So locally you have, by the implicit function theorem, you have x2 is a function of x1 and the input, and x1 dot is it's an ordinary differential equation. You don't have that, but locally it exists. And that's sufficient to prove the optimality system for the nonlinear case. So this is the optimality system for the nonlinear case. And if you look at it, I'm not going to dwell on this. If you look at it, you see that these are the Jacobians, and its implicit function theorem plus optimality put together gives you this optimality system. Now, that's wonderful because then you can locally solve the boundary value problem using some boundary value solver, but you have a problem. This system is obtained by the implicit function theorem. For the simulation, we could go step by step, and it was done locally. So this part you can get. But the adjoint equation that you have here needs also this information, but that you can only get once you have done the implicit function theorem for this one. And that's a problem. And for a while we were pretty frustrated about how to do this numerically, until we noticed something which I will show you in a minute. So first of all, I should say these are local results, local in the neighborhood of a solution because you use implicit function theorem. All the results work also for general non-square, so everything's possible here. Endpoint condition can be included for the x, and you can also put input and state inequality constraints, but it gets terribly technical to write this down, so you really have a maximum principle of Pontryagin extended to this general situation. So for the numerical method, as I mentioned, in the implementation of the integration codes, we use we can use non-smooth projectors because we don't do a change of variable. We have the original variables in there. And so we don't need to have smooth projectors. So we don't need to take the manifold and smoothly find a coordinate system that smoothly varies. And that's great because computing these projectors, for each of them you would have an extra differential equation that you would have to carry along, and that's an n squared differential equation. So if you have a million already equations, so now we are talking in a million squared equation. And that's not something you want to do. So in the forward simulation, it's enough to know the existence of such a smooth projector, and then you just compute it locally. So because Runge-Kutta methods or BDF methods don't see such a projection. But the adjoint variables, they depend on these projections and their derivatives. So we cannot use this approach for the optimality system. But the nice thing is, even though Z1 and Z2, which pulls out the differential and the algebraic equation, are not smooth, Z1 transpose, which is an orthogonal projector, that's smooth. And so as a consequence, there is some smooth information there, even if you work non-smoothly. And so what you do is you introduce some new variables. So you need this term in the differential equation, and so you put a Z1 in here. You put a Z1 transpose in here. Then Z1 transpose Z1, that is a projector, times lambda 1. And you call this Z1, lambda 1 you call lambda 1 hat. And the same thing for the other variables. So as a consequence, now you have a smooth projector in here, even though the Z1 is not smooth. And but you have to add the condition that the lambda 1 is in the range of that Z1. And so you compute locally a QR or SVD computation or something similar to get these conditions. So you add this to the system, then the optimality system looks like this, and you have two extra equations. And now all the quantities are available for all time steps. And then you can apply Gauss-Newton solver. Here's a very simple mechanical examples like the one that I had. So it's a motor-controlled pendulum. So you have gravity and you have a controller sitting here. And now you want to control this. This is a test case. You can show that it satisfies the hypothesis with mu equals 2, 3 algebraic equation, and 2 differential equation, no vanishing equation. Use a DAE or a boundary value solver that we designed. And you can see this is Gauss-Newton method for the optimality system, and you can see that it nicely converges. It takes a few steps, and that's because we usually don't know a very good initial guess, and the Newton method has to get into the range of where it converges. And the optimality of the cost function is correct up to discretization and round-off errors. So now let me come back to my two examples in the beginning, my real-world examples. So here are some results from this collaborative research center. First, let's look at the model problem. The problem of moving this recirculation bubble around. And so we did that with a loudspeaker. We put a loudspeaker in the step, and we put high oscillations or low oscillations in the step. And the second part is to reattach these things to the wing. So here is an example. So we just took a flow solver and put our controller into the flow solver. So this is here a desired position where you want. So I want the middle of the recirculation bubble here, here, here. So I always switch where I want it. And then I let the controller fix it. So it needs a few oscillations, and then it fixes it. So this is 2D on the model, but we have implemented it in the channel in 3D. And if you really move this around a lot, you can see this, and you can hear it in the room. So the loudspeaker makes a lot of noise to move this recirculation bubble around. And the controller looks like this. So that's the control function. So it does some oscillation, and then it gets it. So that's very nice. So this is an Airbus Wing. And our colleagues from engineering drilled holes here in the flap. And so that we can blow or suck air out of these things. And so the first thing we did was lift optimization. That was not optimal control, but optimizing the lift. And you can see that depending on the angle of attack, the lift coefficient can be highly changed here from 2.2 to almost 3. That means with this little effort of blowing and sucking air, you can have a much higher lift in the airplane. This has been now put into a glider that is operating in the World Championships for long-distance gliding, and it's illegal, but you cannot use it in a competition. But you get much, much further using this actually with a lift. And here are some examples. So here's the flap. So here the flow detaches from the wing, and then we blow air and pull this flow back to the wing. This is numerically and experimentally done on this wing, Airbus Wing. So now I come to the automatic transmission, and one should really be honest about it. This was a complete failure. Why? So 9 PhD students at Daimler worked on this problem. They put together, they had a prototype that was built, cost 10 million euros to build the prototype, 30 million real. And you build this thing, and you do all the measurements. My group was supposed to do the controller. Some other group was to do the simulation of the hydraulics, the simulation of the thing. So we did every part separately. It was modeled, it was simulated, and it worked perfect. We put everything together, and nothing worked. Now, this it's bad from the first point of view as an engineer, but it's very good because it shows what the difficulties are. Just modeling pieces and putting them together is not the story. This will need a while. So fortunately for us, I was supposed to do the control, and I could do the measurements on the real prototype. So the control we could do. So here's the variator. These parts are pushed together, and then there is these two cones that are pushed back and forth. And here is measurements is in red, and simulation of our reduced model that we got from input-output data. And we got these peaks pretty good. I mean, there are some deviations here, but that's always in such a physical model. And this is the pressure at the way these two conic parts pressure on the other conic part. So that's also pretty good. And here is the controller that we built. Now the controller doesn't, so that's the red curve is what you want. That's the desired control. And the blue curves is what we got. Form a model that didn't use any of the modeling. It just input-output data. So we built such a controller, and for the pressure, it's fine. For the control voltage, we have quite a big difference here. But that's what you will buy when you buy a new Mercedes S-Class in 2015 or 16. So let me conclude. Automatic modeling is becoming standard in industry. And let me add, in 1869, Kirchhoff gave a talk at the Academy of Science of Germany at that time, Prussian Academy of Science, and Kronecker was in the audience. That was the start of differential algebraic equations. And in the beginning of the 20s, it was completely abandoned because the problems that you could solve were so small that you could do it analytically. In the beginning of the 70s, with the advent of circuit simulation, automatic circuit simulation, the DAEs came back. The same equations that Kirchhoff wrote down in 1886. And it was quickly realized that there are some problems with the numerical simulation. They have now been solved in the circuit world, but they have not solved in the other multiphysics world. So what you have to do is you have to reformulate the automatically generated code so that they're good for numerics and control. And now for the simulation, we pretty much know what to do. For the optimality condition, we just have found the correct optimality conditions. They are very special self-adjoint boundary value problems. Is that a surprise? No, because there's an old result of Liostanik. Every optimization problem, the KKT conditions have to be some kind of self-adjoint operator, but you have to find the right spaces where this is true. These structures generalize the structure of Hamiltonian systems, and they generate symplectic flows on some manifold. But the manifold is not known, so you have to generate it. And that is a problem. And for the real-world problem, to put this on a board computer or into the airplane, you have to do reduced models, and that is still a challenge. So we're working on model reduction for these kind of things, and it's still a big challenge. So with this, I would like to thank you.